Up last, we have Zachary Ruff with ShinyPNWCnet, AI-powered desktop audio processing for biodiversity research and monitoring. Thank you.
Okay, I'm glad you had to say that and not me. Also, this is terrifying, and shout out to all the other presenters for not showing fear. All right, so I'm Zach Ruff. I work for Oregon State University. I'm going to be talking about this little program called ShinyPNWCnet. And shout out to my co-authors in this work, Damon Lesmeister and Julie Jenkins of the U.S. Forest Service, and Chris Sullivan, also of Oregon State. So ShinyPNWCnet is a Shiny-based desktop application to process audio data for purposes of bioacoustic research and wildlife monitoring. It uses a deep learning model that we developed called PNW-Cnet to automate the detection of sounds produced by a whole bunch of target species at this point, but most notably northern spotted owls. It facilitates review of those automatic detections. It's really designed as just one piece of an overall workflow. So it's not like a fancy application that does everything for you, but it's designed with the assumption that you have some acoustic data and you want to do ecological analyses with them. And it's designed to get you from point A to point B in a minimally atrocious manner. So I wanted to give a little background and motivation. If you're not familiar, this is the northern spotted owl. It's a subspecies of owl that's endemic to the Pacific Northwest. It is federally listed as threatened and has seen major population declines throughout its range since the early 20th century. And in response to those declines, there was an executive action in the mid-90s called the Northwest Forest Plan that basically halted logging on about 25 million acres of federally managed lands in the Northwest. And this was an enormous intervention to, try and protect northern spotted owls and to try and assess whether those interventions were having the desired effect. It also mandates ongoing monitoring of northern spotted owl populations, and that monitoring is still going on to this day. So this may or may not be an obvious point, but owls are actually kind of hard to study in the wild. They occur at pretty low population densities, often in these sort of vast, rugged landscapes. They're very well camouflaged and they're very reclusive, especially during the day. They're usually just hunkered down like in holes in tree trunks. So if you just go out and try and look for owls, you're not going to find any. The only thing that makes this somewhat feasible is that most owls are very highly vocal. They have these very distinctive calls that they use to establish territories and communicate with each other, and we can identify them by those calls. So historically, owl monitoring relied on what's called a callback survey. So you go out, you play recordings or imitations of owl calls. This provokes a territorial response from real owls that are nearby. They call back to you, hence the term callback survey, and that response is how you detect their presence. Now this approach basically works, and it was the foundation of spotted owl monitoring for a good 25 years. But this species has continued to decline, and as it declines, there are issues with this approach that became kind of more and more difficult to stomach. And so a few years ago, we started looking around for an alternative approach. And the alternative approach that we came up with is what's known as passive acoustic monitoring. Sorry, we didn't invent this, but we landed on it. This relies on automated recording units, or ARUs. So these are rugged programmable audio recorders that you can just strap to a tree and leave out in the woods for extended periods. You're not provoking a territorial response for this, hence passive monitoring. So it's a lot less invasive to the birds. They just capture whatever is going on around them while they're recording. And they can stay out for like hundreds of hours worth of recordings. And so they can stay out long enough that basically anything that makes noise out in the woods is going to show up in your recordings eventually. We did a pilot study back in 2017 that turned into this paper by Leila Dukac, and we found that this method works really well at detecting northern spotted owls. If you have a field site that owls are using and you deploy 4 ARUs to record about 6 hours a day, or 8 hours a day for about 6 weeks, you have an over 95% chance of those owl calls showing up in the recordings at some point. So it's very, very reliable at detecting them when they're present. So it's great. What's the catch? The catch is that you wind up recording just truly enormous volumes of data. We deployed ARUs at about 30 field sites in that 2017 study, and we wound up recording about 150,000 hours of audio, which is a lot. And yet looking back 6 years later, we record like 2 million hours of audio a year now. So it's it can easily run away from you. Be careful. So you really have to treat data management as a full-time job. You need also some kind of automated detection to find the calls of the species that you're interested in within all those data, because there's way too much to go through it all manually. And you have to make sure that that automated detection is reliable, because especially for a species like spotted owls, there are ecological and potentially legal consequences to, if you falsely conclude that they are absent or falsely conclude that they are present. So what we did is we took owl calls that we had found during the pilot study and used them as a training set to train the first version of what we now call PNW-Cnet, which is a deep neural net that detects sounds produced by our target species in spectrograms. So a spectrogram, if you don't know, is a visual plot of sound energy as a function of time on the x-axis and frequency on the y-axis. And a cool property of spectrograms is that distinctive sounds tend to translate as distinctive visual patterns. And that turns it into an image classification or an object detection problem, which deep neural nets are really good at. So you feed spectrograms into the neural net, and for each image, it spits out a set of class scores. Each of those is basically a prediction of whether each class is present in that image. I'm going to say class. Classes loosely correspond to species. We have some species that have more than one class because they have different call types, but that's how you can think of it. And for this set of class scores, you can just apply a simple threshold and say anything that scores above 0.95 is an apparent detection for species X. So we've developed a workflow around this where we have field sites that each have multiple recording stations. So you deploy ARUs at those stations, leave them out for 6 weeks or so, collect your data, do all your data organization and standardization and QA/QC and stuff. Then you process the data, you convert it all to spectrograms and feed the spectrograms into the neural net. The neural net basically gives you a set of apparent detections for all those different target classes. And what we do with those apparent detections is a bit of manual review. We don't review everything, but we review a subset sufficient to basically confirm whether or not species X is present at station Y in recording week Z. And that allows us to construct a weekly encounter history, which forms the basis of occupancy modeling, or you can use it for other ecological analyses too. And a nice side effect of that review process is that you get more training data out of it. You get annotations that tell you kind of where and when each species is present in each clip. And we've been able to use those to periodically retrain the PNW-Cnet model. So back in 2018, we had a very simple model that just detected a few species of owl. Whereas now we just trained version 5 actually and detects something like 75 species of birds and mammals that are found in the Northwest. So it's gone from a very simple model to something that you can actually use for wide-scale biodiversity monitoring. So that's great, and it works for us. Why did we build an app, which I have not addressed yet? So bioacoustics is kind of hot right now. A lot of people have seen the promise of the approach. They're investing in it. And that investment has not always come with a lot of forethought about what they're going to do with tens of thousands of hours of data at the end of their field season. We have gotten a number of requests over the years to process people's data for them, but like there's nothing magical about the way that we process stuff. So if we just distribute the tools and methods that we use that we know work, then it's kind of the metaphor of teaching people to fish rather than giving them fish, right? We get a lot of same benefits, but we don't have to do as much work. And we felt that a GUI would be more appropriate, more approachable for the type of person who would be interested in this, which is typically a wildlife biologist. They're smart, capable people, but their expertise is not necessarily in computers. They're not necessarily comfortable running stuff from the command line. So we figured that that would be a little friendlier to them. So what we've wound up with is this program, ShinyPNWCnet. It is freely available through my GitHub page. It requires a few external programs, but it's stuff that's either nominally free or it's stuff that you already have if you do wildlife work. We've been documenting the neural net and the associated app in peer-reviewed publications. This is like the slowest and most cumbersome way to get the word out about this stuff, but it gives people something to cite, and hopefully the more they cite it, the more visibility we'll have. I might start a newsletter or something. So what does the app actually look like? This is kind of unusual. This is a purely local app. It's just in the nature of bioacoustics that like there's too much data to move over the network. So you want to run everything locally. We just use Shiny as a way to build a GUI that runs on R, and it works pretty well for that. But this is just like bone stock or Shiny default application. But you've got a sidebar with some controls and navigation. Most of these controls are actually disabled on launch, and they become active as you move through this processing workflow to sort of guide you through the proper procedure, which is nice. You find the folder containing your WAV files, you paste it into the little text box, you click check directory, it searches through the directory tree for files with a .wav extension. Oh God, 5 minutes. It enables this process files button. You click that and it starts generating a whole grip of spectrograms. There's 300 spectrograms for every hour of audio. So if you have like 1500 hours, it's going to be there for a while. But once it's generated the full set, it loads in the trained PNW-Cnet model, uses it to generate class scores for each image. That's a spotted owl 4-note location call, which I don't have an example of, and I will not be imitating, sorry. At the end of processing, you get 2 output files out of it. You get a predictions file, which is just the raw class scores for each image, and you get a detection summary file, which applies a range of different thresholds from like 0.05 to 0.99. And says at each of these thresholds, how many images met or exceeded that threshold for each target class, and it bins them by recording station and week. The app will display this graphically, so you can kind of explore where and when you have detections occurring. You can export the apparent detections for a single class if you want, which is a good way to kind of drill down if you're interested in examining something in detail. Otherwise, you use this create review file button, which just exports apparent detections for all the different classes, or at least all the ones you're interested in. You can define a custom set of classes by just providing a CSV file listing the classes you're interested in the order of priority and the score threshold that you want to use for each one. And these review files are optimized for use with Kaleidoscope, which we don't make. It's made by Wildlife Acoustics, but it lets you go through this review file. Each of those rows in that table is an apparent detection. It tells you what the class or the apparent class was, tells you the score. You can sort it in different ways to review these at different levels of detail, depending on how interested you are in each of these classes. So you can review at this level of an entire field site or at the level of each recording station. And you can apply species or ID tags using this manual ID column, and they'll be saved to the CSV file. So, and that produces a set of confirmed detections that you can then use for your occupancy analysis or what have you. And then we have a settings page that just can adjust various aspects of the app's behavior and performance. Again, it's just stuff that's sort of occurred to me, so it's kind of a hodgepodge right now, but if you have an idea, let me know and I'll potentially add it. So it's not the fanciest app in the world. At the end of the day, kind of the best thing I can say for it is that it works and people are in fact using it. Those people are wildlife biologists who work for various government agencies, academic researchers, private companies, NGOs, not the Krakens, I'm sorry, but I thought it would be funny. We held our first training workshop in Corvallis in October. We had a fair amount of interest in that. About 45 people showed up, so that was kind of encouraging / scary. My experience of using Shiny, I have to caveat with, the obvious fact that this is not really what Shiny is meant for. You're meant to use it to develop web apps. But, like I said, you don't want to move this much data around over a network. My experience of Shiny is that it's kind of a pain to use, but you can do a lot of cool stuff with it. But it is kind of a pain to use, but you can do a lot of cool stuff with it. That's all I can say. It does everything R can, which hopefully I don't need to sell you on. The UI is really good once you get it working. It's dynamic, it's responsive. There's a lot of good design just baked in, so you don't have to mess with CSS if you want to, you can. Obviously, people can make it a lot prettier than I have. The cons is that, because it is a GUI, it's just an added layer of complication over literally anything that you want your program to do. So think long and hard about whether or not you want to just make an R package or even just a set of Python scripts, which is what I use for processing. I find Shiny apps kind of hard to debug, but I'm also not super good at debugging, so that's maybe a me problem. In the future, we would like to incorporate that newest version of the neural net. Right now, it's still on version 4, which works fine. But The installation process kind of sucks right now. I would like to streamline that a lot, and I'm not doing a great job at streamlining it, but we'll get to it. Yeah, I would like to produce more documentation videos. I made one as a supplementary material for that paper that I screenshotted like 5 slides back. And that was kind of fun. And I think it was really helpful for a lot of people. So there's that. And then, yeah, just trying to get the word out about the fact that this exists and new features as they're rolled out. So I think a mailing list might actually work pretty well. Right now, it's pretty much word of mouth. So thank you for listening. I would be happy to take questions now or find me later, or if you think of something in 2 weeks, just email me. So, thanks.